Now we are going to discuss two more result of a Laplace transform known as the initial value theorem and final value theorem. So, first we prove the initial value theorem and final value theorem using the derivative property of a Laplace transform. Then we try to solve two numerical problem, one based on a initial value theorem and second one using the final value theorem. So, what is the statement of an initial value theorem? Here already we write the statement of our initial value theorem. Here, as earlier we say that the ft, f dash t, f double dash t, these are under the category of a class A function. So, that is why here we write what? In theorem, if ft and f dash t v of a class A and Laplace transform of a ft equal fs, then limit t tends to 0, ft equal limit s tends to infinite s into Laplace transform of a ft. We may also write this expression as a limit s tends to infinite s, since Laplace transform for ft is a fs. So, we may write s into fs, s into fs. So, how we prove this one? So, in order to prove this one, we use the property of a derivative of a Laplace transform and first order derivative of a Laplace transform. So, by the property of a derivative of a Laplace transform, we able to write what? We able to write this result, means here we write by property of a derivative, Laplace transform of a f dash t equal s Laplace transform of a ft, Laplace transform of a ft minus f of 0. By property of a derivative, Laplace transform for f dash t equal s Laplace transform of ft minus f0. Now, Laplace transform, by the definition of a Laplace transform, this becomes 0 to infinite e to power minus st f dash t equal s Laplace transform of a ft minus f0. Now, taking the limit s tends to infinite. Taking the limit s tends to infinite, then left hand side become what? 0 to infinite limit s tends to infinite e to power minus st f dash t dt equal s Laplace transform of a ft and limit s tends to infinite minus limit s tends to infinite f of 0. Now, if we closely observe and try to find out the limit s tends to infinite e to power minus st f dash t dt. So, if limit s tends to infinite, f dash t is free from s e to power minus infinite. So, this become 0. So, this term, this limit become 0. 0 equal what? 0 equal limit s tends to infinite s Laplace transform of ft minus what? This one is a free from s. So, this one is a f0. So, after simplification, what is the result? Result is a f0 equal limit s tends to infinite s Laplace transform of a ft, and we may also write this one as a limit t tends to 0 ft equal limit s tends to infinite s Laplace transform of a ft. and this expression can be also written as a limit t tends to infinite f, not a t tends to infinite, sorry, t tends to 0, here f t equal limit s tends to infinite s f s, because Laplace transform for f t is a f s. So, we may use this initial value theorem as a formula in order to solve the numerical problem. In a similar manner, there is a final value theorem. Already here we write a statement of a final value theorem. Statement of a final value theorem. What is the statement of a final value theorem? Again, here we assume that f t and f dash t both are under the category of a class A function, means both have exponential order as t tends to infinite, and both are either piecewise continuous or continuous as from t equals 0 to infinite. So, how we prove that? If the f t and f dash t be of a class A function, then limit t tends to infinite f t equal limit s tends to 0 s Laplace transform for f t. We may also write this expression as a limit s tends to infinite s tends to 0 s Laplace transform for f t is a fs sfs. So, how we prove this one? Again we use the result of a derivative. Now, by property of a derivative of a Laplace transform, by property of a derivative, by property of a derivative, by property of a derivative, Laplace transform of f dash t equal s Laplace transform for f t, Laplace transform for f t minus f of 0, minus f of 0. Now, using the definition of a Laplace transform, this becomes 0 to infinite e to power minus s t f dash t dt, f dash t dt equal what? Equal s fs minus f0, minus f0. So, now taking the limit s tends to 0 on a both hand side. So, in the next phase we write limit, taking limit as s tends to 0, as s tends to 0, then left hand side become limit s tends to 0 integrate 0 to infinite e to power minus s t f dash t dt equal limit s tends to 0 sfs minus f of 0, f of 0. Now, we put the limit here, limit s tends to 0, then what will happen here? This become s tends to 0, then e to power minus s t, there is a one term having a variable s. So, limit s tends to 0, then this becomes 0 to infinite f dash t dt, left hand side become this one, and there is a no change on the right hand side, limit s tends to 0 s fs minus f0. So, if we find the integration of f dash t, obviously the integration of f dash t is a ft. So, this become ft. What is the lower and upper limit? Lower limit with the 0, upper limit with the infinite, this become limit s tends to 0 sfs minus f of 0. So, after simplification of this one, first term become limit t tends to infinite ft, and second term become f0, second term become f0, and this become what? This one is a free from s. So, this become limit s tends to 0 SFS minus f of 0. So, this one cancel out, and what is the result? Result is a limit t tends to infinite ft equal limit s tends to 0 s Laplace transform for ft, and this may be also written as a limit s tends to 0 s fs limit t tends to infinite of a ft. So, this may be treated as a what? This may be treated as a what? This may be treated as a formula. This one is a final value theorem. Proved. So, this one is an initial value theorem, this one is a final value theorem, and this one is a initial value theorem. In an initial value theorem, we closely observe limit t tends to 0, initial value, limit t tends to 0, initial value, and in a final value theorem, limit t tends to infinite, limit t tends to infinite, and in a right hand side, in an initial value theorem, s tends to infinite, and in a final value theorem, s tends to 0. So, in order to remember the initial value theorem and final value theorem, in initial value theorem t tends to 0, but s tends to infinite. In a final value theorem t tends to infinite, but s tends to 0. This one is a only difference in term of a expression of a initial value theorem and final value theorem. So, here t tends to 0, s tends to infinite, t tends to infinite, then s tends to 0, and other term ft and sfs remains unchanged. So, this one is a what? This one is a initial value theorem and final value theorem, means how we remember the initial value theorem and final value theorem. And at last, we try to solve one numerical example based on a initial and final value theorem. So, here Laplace transform for ft is already given, then find a Laplace, find a limit of t tends to 0 of a ft, limit t tends to infinite of a ft. So, as we know that limit t tends to 0 of a ft by the initial value theorem equal limit s tends to infinite sfs, and limit t tends to infinite of a ft equal by final value theorem ft s tends to 0 of a sfs. So, in order to find out the value for first one, limit t tends to 0 of a ft, if Laplace transform for ft is a given. So, if since Laplace transform for here Laplace transform for ft, let Laplace transform for ft equal 1 upon s into s plus a. Now, by initial value theorem, initial value theorem, and here we assume that Laplace transform for ft equal 1 upon s plus a, this one equal capital Fs. Now, by initial value theorem, what will happen? Limit t tends to 0, ft equal what? Limit s tends to infinite of s into fs. So, fs is already given. So, here we put the value of fs. So, limit s tends to infinite. What is the fs? Here we put the value of s into fs. Fs is a 1 upon s plus a. So, s and s cancel out. So, what is the value of a limit? 1 upon infinite, the value of a limit is a 0. So, what is the value of a limit t tends to 0 ft is a what? The value of a t tends to 0 ft is a 0. Now, by final value theorem, limit t tends to infinite, ft equal what? Ft equal limit s tends to 0, S into Fs, S into Fs. So, S into Fs again limit S tends to 0. What is the value of Fs? Fs is here we write S, Fs is a 1 upon S, S plus A, S cancel out and limit S tends to 0. Then what is the value for this one? The value for this one is a 1 upon A. So, by initial value theorem, limit t tends to 0, Ft equal what? Ft equal to 0, Ft equal to 0. And by final value theorem, if we write result in a next phase, so limit t tends to 0, Ft become what? Ft becomes 0 and limit t tends to infinite, Ft equal 1 upon A, 1 upon A, 1 upon A. So, these are the two values that is required to calculate. So, this one is a what? This one is a what? This one is a, with the help of our initial value theorem and final value theorem, how we find the value of a limit t tends to 0 of a function Ft, limit t tends to infinite of a Ft. So, what is the summary of this lecture? Here we able to prove, we proved the derivative property, integral property, initial value theorem, final value theorem and solve some numerical example based on a initial value theorem, final value theorem, property of a derivative, property of a integral of any function Ft if we have a Laplace transform for that function. So, this one is all about Laplace transform of any type of a function. So, in the next lecture we find a Laplace transform for some special function and try to find out a Laplace transform for some function using the combination of these property, means derivative and multiplication, division and property of a derivative, like this one, division by t and property of a derivative, or combination of a linearity property, change of a scale property, division by t, multiplication by t and integral property or derivative. So, we combined more than one property or more than means all the property or some properties in order to find out a required Laplace transform of any combination of any function. So, by using these property we try to solve the numerical examples. So, I hope all of you enjoy the series of a lecture of Laplace transform. I hope this lecture will be helpful for your GATE examination, NET examination and if you are preparing for any other competitive exam. So, thank you watching my lecture. Thank you very much.